So, welcome to the lecture of this finite volume method. Now, the third one we will look at the central difference scheme. Now, the central difference scheme, the truncation error, to obtain that it requires some sort of a little bit involved calculation, because it uses the stencil from the both the sides. So, what one can introduce in the calculation, let us say we have phi e minus phi w, which is nothing but half of phi e plus phi c minus half of phi c plus phi w, which is phi e minus phi w plus the truncation error. So, this is the exact term, this is what interpolated. Okay. So, assuming the velocity is known everywhere and again the grid is uniform with size delta x. So, we can write these things in this fashion. So, the T e here is nothing but the truncation error. So, now we use Taylor series expansion to find out all these terminology one by one. So, the first one we get phi w is phi at small w or face w minus del x by 2 phi w prime plus del x square by 8 phi w double prime and so on. Now, phi c equals to phi w plus del x by 2 phi w prime plus del x square by 8 phi w double prime and so on. Phi c again can be represented phi e minus del x by 2 phi e prime plus del x square by 2 phi e double prime, and phi e is so nothing. Now, what one can do, that if you get the average of this term, half of phi e plus phi c, which could be phi e plus delta x square by 8 phi e double prime plus delta x 4 by 384 phi e, like that, which is delta x square by 4 phi e double prime equals to phi c minus 2 phi e plus phi e minus delta x 4 by 192 phi e 4. So, that is what we get. Now, similarly, you get this term half of phi c plus phi w, which will be phi w plus delta x square by 8 phi w double prime plus delta x 4 by 384 phi w prime. So, which one can write delta x square by 4 phi w double prime equals to phi w minus 2 phi w plus phi c minus del x 4 by 19254 phi w. Now, you substitute this term and what you have got here in the discretized equation. So, what we get phi e plus phi c minus half of phi c plus phi w, which is going to be phi small e minus small w plus delta x square by 8 phi e double prime minus phi w double prime plus del x 4 by 384 phi e fourth derivative minus phi w fourth derivative. Now, one can expand this small phi e in terms of phi c, which is also like this: phi c double prime cube by 48 phi c triple prime and so on. So, one can represent that phi c minus del x by 2 phi c prime plus del x square by 8 phi c double prime and so on. In addition to that, similarly one can write phi e equals to phi c plus delta x phi c prime, delta x square by phi c double prime, so on, and phi w equals to phi c minus delta x prime, delta x square by 2 phi c double prime, so on. So, in terms of cell center value phi c, you can expand, or rather you can actually obtain all this expression. Now, we got this set of information, another is this. Now, in this set of information, if you put these things there, like phi c minus 2 phi e plus phi e. So, this term and this term, if you do that, then what we get? Phi c minus 2 phi c minus delta x phi c prime minus delta x square by 4 phi c double prime and so on, plus phi c plus delta x phi c prime plus delta x square phi c double prime and so on. So, which will simplify to delta x square by 4 phi c double prime plus delta x cube by 8 phi c triple prime and so on. Similarly, one can write phi w minus 2 phi small w plus phi c, which will get you del x square by 4 phi c double prime minus del x cube by 8 phi c triple prime and so on. Then one can compute phi e double prime minus phi small w double prime as del x square by 8 into phi e double prime minus phi w double prime equals to del x cube by 8 phi c triple prime plus del x to the power 5 128 phi c fifth term. Now you substitute back everything in that equation of half of phi e plus phi c minus half of phi c plus phi w, which will be phi e minus phi small w plus del x cube by 8 phi c triple prime plus delta x 5 by 128 phi c fifth term. Now you divide by delta x, then the truncation error term will be order of delta x square by 8 phi c triple prime plus delta x 4 by 128 phi c 5 and so on. So, this we divide by delta x, you get this truncation error. So, which essentially shows that the higher order term is order of delta x. So, CD is second order accurate. So, that is what it turns out. So, CD becomes second order accurate scheme. Now, so this takes care of the accuracy. Now, the other point which comes to that thing is the stability. Now, the confusion related to truncation error, first order for the physical solution and second order for the unphysical one, has led to extrapolate this term so accurately that the diffusion gets reduced. Now, at the same time, while doing that, one has to also keep in mind the stability of the system, because while doing that these things, stability can be also affected. For example, if one takes this kind of a tensile like this, C east west, so this is W face, so this goes in this direction, this is UE, UW. Now, the quantity here is phi W, scalar here is phi C, here is phi E. Okay. Now, if I look at the change of this term is nothing but del x rho u phi plus del x gamma del phi by del x plus source term. Now, this left hand side is the rate of change of phi c and the right hand side shows the net influx across the element surface. So, if the numerical error exists, then the right hand side may increase or decrease depending on the situation. Now, if in an unstable scheme, a small deviation from the correct value of the phi c gives a corresponding increase or decrease in the net influx at the right hand side. So, when an iterative procedure is used as a part of the solution mechanism, an increase or decrease in the net influx will further increase or decrease the value. So, either increase or decrease in the net influx will have the similar impact on the solution of the phi c at each sub iteration step. So, in a stable scheme, this change in phi c is due to the errors in the right hand side, and that should feed back negatively into the right hand side as a self corrective device. So, for this kind of numerical stability, what one has to do, the right hand side with respect to phi c should be less than 0. So, that is indicating the sensitivity of phi c in the combined system. Now, if there is a increase or decrease in phi c, which will correspond to increase or decrease in the influx, which will also in turn pushes phi c downward or upward to correct the value. So, it is a self correcting situation. However, the stability should not be confused. So, stability has nothing to do with they are not same, the boundedness or accuracy. So, stability is something whether the stable numerical scheme could actually be unbounded or giving rise to some overshoot or undershoot or oscillations, wriggles, or can be very diffusive, okay. Also can provide the solution with lower order of accuracy. So, stability here refers to the controlling the numerical error to remain bounded in order to not to increase infinitely, so that the system or the numerical code actually diverges. So, this has nothing to do with boundedness or accuracy. So, stability is something that one has to. Now, keeping that in mind, if you look at that discretized right hand side of the previous equation, the right hand side was minus rho u del u at east face phi e plus rho u at the west face plus gamma del y by del x minus phi c minus gamma del y by del x w phi c minus phi w plus q c v c. Now, one can use CD scheme, then the right hand side for CD scheme it will become rho u del y e phi e plus phi c by 2 plus rho u del y w phi c plus phi w by 2 plus gamma del y by del x e phi e minus phi c minus gamma del y by del x w phi c minus phi w plus q c v c. Now, once if you analyze this scheme, the criteria which is found for the diffusion term that is sensitive to that is the right hand side CD diffusion term by del phi c is 2 gamma del y by del x, and so there is a negative sign to that. And similarly, if someone look at it, the right hand side for CD, the convection term it gives minus half of m dot E plus m dot W. So, for steady flows, which is essentially 0 for steady flows, but not necessarily it will happen for the unsteady case. For unsteady situation, its value will be positive for decelerating flow. Now, in general flow, such regions will act as an Rigel sources and can easily lead to some sort of a numerical failure. Okay, when the Pictet number is large. So, but even for steady flows, as its value is 0 here, for steady flow this value is going to be sort of 0, it cannot fit to the self correcting system. So, what it suggests that steady flow, the net convective flux computed using the CD scheme is some sort of independent of phi c. So, therefore, this will result in same net convective flux over centroid C. Now, similar things one can find out for the upwind scheme. So, the right hand side for upwind scheme will be minus m dot E 0 phi c plus minus m dot E 0 phi E minus m dot W 0 phi c plus minus m dot W 0 phi W plus gamma is by del x E phi E minus phi c minus gamma is by del x W phi c minus phi W plus q c. So, what one can get the right hand side for convection upwind scheme by del phi c is m dot E 0 minus m dot W 0, which will be either negative or 0 for all flows, So, it will be 0 when both the mass flow rates are negative, and a situation that does not arise in one dimensional situation of constant area cross section, but when added to a false diffusion into the induced by the first order approximation, it indicates that the scheme is very stable. So, that suggests that there is a stability. However, this can be achieved at the expense of some sort of an accuracy. So, this is always first order accurate system. So, though it is stable, but it can come with a price that. So, now the other one which is there is the downwind scheme. So, the downwind scheme, the right hand side one can write the downwind scheme is equals to minus m dot E 0 phi E plus minus m dot E 0 phi C minus m dot W 0 phi W minus m dot W 0 phi C plus gamma is by del x E phi E minus phi C plus gamma is by del x W phi w minus phi c. Now, the sensitivity analysis leads to that the right hand side due to phi right hand side of downwind scheme for the convexing part, which will lead to minus m dot E 0 plus minus m dot E 0. This would be minus W. So, that is m dot W. So, the contribution from this guy and the contribution from this guy will come, because again if you look at this term, this is either always positive. So, this is always positive or equals to 0. So, that means for all sort of flows. So, when this is added to anti-diffusion effects, this means this whole term is, as long as it is 0 there is no problem, but when it is positive and it is added as anti-diffusion effect, these things becomes, or rather it leads to the highly unstable scheme. So, one hand you get the upwind scheme which is stable, but lower order accuracy. CD scheme has some sort of a problem, and this guy is unstable, and then so the issue is that this is also, by the way, first order accurate. So, that is where, since as we said, the trade off between two component, one is stability, another one is accuracy. So, highly stable scheme can be completely providing or can completely give inaccurate results, which happens with the CD scheme, as we have seen that for one dimensional case. But accurate scheme cannot be, not necessarily always be stable, or at the other way around also, the stable scheme like the first order upwind cannot be accurate, or so the upwind scheme is stable, but does not provide accurate solution. CD scheme is highly accurate, but it does not provide a great level of stability. So, these are two important things where one has to make a trade off between stability and accuracy, and the scheme that we have seen so far, that is what happens, and carry forward the discussion. Thank you.